Okay.
Everybody, this is Pete. Pete is a senior consultant for artificial intelligence and robotics at the Texas Robotics and Automation Center Laboratories. And he's giving a talk on the case for HAL 9000 for Lunar Outpost. So Pete, please take it from here.
Okay, thank you. Thank you. I'm Pete Bonasso. With this title that everybody heard, case, a HAL 9000 for a Lunar Outpost. So first HAL.
Open the pod bay doors, HAL.
I'm sorry, Dave. I'm afraid I can't do that.
What's the problem?
I think you know what the problem is just as well as I do.
What are you talking about, HAL?
This mission is too important for me to allow you to jeopardize it.
I don't know what you're talking about, HAL.
I know that you and Frank were planning to disconnect me, and I'm afraid that that's something I cannot allow to happen.
So that's what people remember about HAL 9000, a paranoid AI for sure. But what was going on in the whole part of the movie with HAL is that all this was going on. It was managing the spaceship. It was managing life support and communications, the avionics, and then it had a robotic arm and a couple of space pods, and that was all being managed by HAL as well as the pod bay doors. That was 68, and 52 years later we have CASE, stands for a cognitive agent for space exploration. I just want to say that I'm not the only one that worked on this project. So here are several of our contributors. So the motivation for an agent is that when we exceed the normal turnaround time for communications, mission control is not going to be able to manage us like it manages the space station. Now the moon's not going to be quite as bad, but I know that we're going to work on delays so that we can see what it's like to talk to a place as far away as Mars. So the idea is bring mission control along by imbuing a cognitive software agent with the information and knowledge that mission control has. An agent that can generate plans, monitor the systems and notify the crew if there's an anomaly or take care of it itself, control not only robots, but also the processes on space station. Or in a planetary base, this can be talking about a lunar outpost or a Martian outpost as well. And probably very important, more importantly, is communicate interactively with the supporting crew, like we saw HAL 9000 do, although without the histrionics. So as a backdrop, we've been working on a partial gravity scenario. 2 years ago, it was Mars, then Artemis came along. So we just mapped our textures to make it look like the moon, but the basic idea is the same. You're gonna have a set of crew with certain talents and capabilities that's gonna try to establish a base. In our simulation, we have solar panels that provide power to batteries. The batteries then hook up through converters to the power strings of the habitat and also to be able to charge the robots. We have two types of robots in our sim. One is the pretty standard EVA rover with an atmosphere for the crew to exist in as they do extracurricular activities. We also have what we call our TRACLabs that we developed with NASA funding over the years that are little platforms with 2 7-degree of freedom arms and stereo cameras. And they work around the base like this one, controlling a control station that makes switches between the various electronic components. We also have a simulation of the internals of the habitat with regard to life support. We call it Biosim. Biosim has been used in a number of studies. We developed it when we were working on the life support systems at NASA, and it can manage and generate whole days worth of processing of air and gases and water and waste products. And it can also break out a separate atmosphere to simulate the rover that has an atmosphere inside it when the crew's inside it. So we have a pretty nice backdrop. So I give you that as the backdrop as I want to describe the case architecture. The backbone of the case architecture is the planning and execution system. Case has an automatic planner. You provide the planner with goals and it generates a plan that meets all the requirements and doesn't violate any safety constraints. And the actions, the low-level primitives that execute the plan are actually procedures that are developed by the using community. In our case, we use procedures developed by a system called PRIDE, and it has an execution agent that takes these procedures and can execute them autonomously or can execute them interactively with the crew. And these procedures are tied through the electronics to the control system that's being controlled. So this is basically the three-level environment. Problems happen in the control. Often the procedures can take care of them without going back to the planner. But when the procedures finally fail, then the planning system replans another set of actions, either abandons certain goals or changes the way it solves certain goals in order to continue with the mission. So it's a planning and replanning system with a robust execution system. Here's a close-up of one of our planning GUIs. You drag and drop the selected actions from the available actions. You press a button and the planner generates a plan. It's shown in 3 different ways in this sort of a navigator view, in an activity timeline that's color-coded by the agents carrying out the various steps, or by this plan tree, which starts at the top saying do everything, and then it says do these things in sequence. It eventually comes down to the lowest level actions, like prepare your suit and don your suit. And these actions are executed through our PRIDE system. Now, PRIDE is called the Procedure Interactive Development Environment. It has an authoring system. What you're seeing on the left here is the view of an executing procedure. And as I mentioned, it has an execution agent underneath that can connect with the controls of the system being managed. We've been using PRIDE at NASA for a number of years. The Sierra Nevada Corporation is using it on its Dream Chaser program, excuse me. It's used all over the world by the oil and gas industry, and recently Dow Chemical is using our PRIDE system. Try to give you an idea that this is a system that's actually being used every day by people, and it's part of the 3T system. Now, nothing would be working very well if we didn't have a database, and especially a smart database. So we have basically what's called an ontology. It's not just the data about all the systems and the pieces on the system that's being managed, but also the relationships among all the pieces that are being managed. So if a toolbox, for example, is moved from one place to another, the system updates the location of all the tools in the toolbox automatically and makes sure that everything is consistent with regard to where things are and how they relate to each other. So this ontology is served up to all the pieces of the system. As we execute the system, it is automatically updating the database, updating all the references and the relationships, and so that as it's going through its execution, everything has the most current data. Finally, we include that we have been able to use this system not only for avionics, but also for robotics and for the control of life support systems. We used it for a 2-year experiment with a water recovery system continuously at NASA Johnson Space Center. So I want to give you just a video of how this looks running. We have 2 computers running the system. One computer has most of CASE on it. The other computer has the lower level PAX execution system, as well as the simulations running. I'm sorry, you can't see this too frequently. That's the planner. It starts to execute, and the execution is to launch these procedures. This is PRIDE view showing procedures that are being launched. And the first thing it's trying to do is give the habitat power by connecting a battery to one of the DC to DC converter units. And it does that by commanding a robot, one of the TRACLabs, to do a proper knob turning to select first the battery that's going to be used, and secondly, the DDCU that's going to be used, and then it finally connects them together. These robots are the TRACLabs I mentioned, and this idea of a control panel for switching It's just something that came out of one of the studies that we had noticed that NASA was doing. So you have selecting the battery, turning the knob. All of this is being run by the planner. No human is driving this. Then they select the DDCU. It's actually the other arm that's used to select the system that's going to be powered. And you see here in the picture, the arm is using templates for motion and grabbing that we developed called the Craftsman system. That's also being used at NASA in their robot development, laboratories. Once it's done, then it actually makes the connection, and we now have power to the life support system in the habitat. Then the planner, Pride tells the planner these things are done. The planner comes up with new tasks that have to be done. They showed there in the procedure viewer. The green items have been accomplished and the blue items are ready to go. So the GUI is updating, and the timeline, this timeline is probably the kind of thing that people would be looking at more than those task trees. Now, while it's doing these switches, RPCM or switches, it's also told to navigate one of the TRACLabs to Rover Bay. And so that's going on simultaneously, being run by the planner through the Pride system. A procedure for driving the robot is actually being executed autonomously. So you see both the navigation and one of the electronic procedures running simultaneously. So the other thing that's pretty important by one of these agent architectures is a way to manage the running processes on the computers. I showed you different processes running on 2 different computers. When you're running in a station or on a planetary base, it's certainly possible you might lose one of your computing capabilities, or one of the pieces of software might lock up. So we have process manager, intelligent process manager on all the machines that know how these pieces connect. So if something goes wrong, it knows how to notify the other pieces, shut them down, reconstitute the broken piece, and then bring all the other systems up. For example, this Ontology server, which, as you can imagine, feeds a number of processes all throughout the case system. If that were to go down, all these connections that you see here would be notified to disconnect and then reconstituted. Here's an example of that happening. I know it's hard to see, but the Mac on the bottom left is running a lot of the processes, as I indicated in the previous slide. And this user, me, is going to go to the Ontology server and just kill it. I mean, forcing the process managers to start figuring out what to do. And they notify all the systems that depend on the Ontology server. They bring them down safely. Then they bring the Ontology server up and start to reconstitute all the other systems. One of the systems that was running over here on this computer was a resource manager that's monitoring all the resources as they're being used by the planner and the agent, and will send alerts if something is going below critical data points. So the resource manager starts up again. And then in the rest of the case system, we see the PAX agents, they're called execs. AP is our planner, the adversarial planner. And eventually they all come up and the planner GUI that was there before comes up. And we've basically reconstituted the system with very little effect on all the processes. So an important thing, as I mentioned at the beginning, is to be able to interact with the user. So we have a dialog management system that is connected to all of the case systems so that you can talk to it about any parts of the system. And probably one of the biggest important things about it is all the dialogue generates the concepts from the ontology. So our dialog manager is pretty robust when it comes to the lunar base or the Mars base. But if you were to ask Case who was the president of the United States, it would have no idea. So the power of our dialogue system is that it knows everything about the thing it's running and almost nothing about anything else, so it's very fast. Here's an example interchange. Case says, what can I do for you? The user says, send the rover to waypoint 1. So now dialogues are designed to figure out the intent of the user and the details of the intent before carrying out the action. So the system says, I have 2 rovers. I don't know which one you're talking about. You tell the system and it sends it off to the rate point. Particularly in this case, it would probably just start a procedure up like you saw running earlier to move the TRACbot. Then it asks you again, what else can I do for you? You can start the thermal control system and things like that. Important thing we've done in the last few years is turn that around into a voice recognition and speech synthesis system. We've used the Chrome's web API for the speech, and we use Vue.js to develop a top-level display. Because we believe instead of looking at all these different displays, the user is going to want basically a top-level display and a voice interaction, so the user can be following along easily, and if something starts happening, they can look quickly at the top-level display and interact with Case to talk about how to take care of any problems that come up. Now, I'm going to show you in this video how we talk to Case about executing a procedure. The voice interaction is in the upper right, but I also have the Pride view up, and you'll be watching it run. Now, the idea generally is the user doesn't have to watch the procedure. Case tells it everything that's going on, explains what to do, and the user does it. But it's good to see in the background the procedure executing as you interact with the system.
Hello.
That's me.
Hello yourself. Winking face.
How are you?
The process manager is down, but I am fine. Thank you.
Start the rover prep procedure.
Starting rover prep procedure.
So now
Preconditions. This is just information. Say okay or go on.
I'm going to bring up the procedure. So when it's just information, it explains what you have to do. Then it doesn't repeat that the next time there's information.
Okay.
For surface segment only, NSS and NIRVSS can be on prior to D1 information.
I like her voice better than HAL's.
I'm afraid I can't.
Announce overdrive preparation activities are about to begin. This is a manual instruction. Say done or stop.
Done.
Safety-related flight rules above oven stowed, lava stowed, drill stowed must be explicitly verified on the loops information.
Okay.
Record overseas go, no go. This is a record instruction. Answer go or no go.
Of course, it's record, not record.
Record payload go, no go. A record instruction.
And then you can actually type in the information if you care to. So that gives you an idea of how we interact with Case. We did a number of experiments in the research, and we were able to manage this lunar base successfully during a 4-hour scenario that included the EVA rover going out and doing an EVA. Some of the anomalies we handled were an O2 leak in the rover. And when you have that, the IVA, the internal vehicular activity person who's monitoring from the habitat, can tell the crew, come on back or get in your suits and continue the EVA. We also had CO2 that was rising in the cabin unexpectedly, and they had to really go through a lot of things to figure out if it was the CO2 removal system's desiccant beds, or the fact that too many people were exercising, or was there an actual leak in the cabin. We used this dialog system, as you saw, with a number of test subjects, conducted an engineering experiment, and they all enjoyed doing that, but it was surprising to see how people used it. Some people just used the voice interaction, just that one blue screen with the voice, because they could scroll back and see what was said and what had happened, and basically in their minds figure out what they had to do. Other people just liked it as a backdrop. They liked the high-level display. The voice was sort of in the background. They almost let that be an information system to their ears, but they more like the mouse interacting with the various displays. So in general, something like a Case provides a real feasible approach to agent design and it's for exploration because we're leaving mission control. If you fill the agent up with procedures that have been developed from mission control and developed, of course, during simulations about the lunar surface or the Martian surface, we basically have a system where you can build the agent that you need for whatever you're trying to do. It provides onboard autonomy that's really important because we don't want the crew spending a lot of time managing their own life support. We want them doing the tasks and the jobs on the habitat. But if something does come up that's off nominal, they can work with the agent to come up with a solution. As I mentioned with the process manager, it's robust in the face of computational failures. And we provide the crew with both a voice recognition and a text-to-speech interface. Lots of times I'm asked, well, why don't we just start using it? And so I'll ask, is it ready? The biggest thing that makes it ready, let's say 2/3 ready, is that it runs on user-developed and vetted procedures. As I said, we have already used Pride and the developed procedures for the space station. The Dream Chaser people are using it. Most recently, a company called Intuitive Machines, who's building a lunar lander for the Artemis system, is using Pride. So once you develop and vet the procedures, 2/3 of the system is ready to go. Now it generates plans automatically, and often those plans, all the plans are valid. They don't violate any problems and they get the job done within the time constraints. But sometimes users have a preference for where they want the planner to put its emphasis. That's something we would have to work out with the users through simulation systems about the moon or Mars. Once we go to the moon, we can start developing those kind of things, generating different plans that the actual users running the base want to see. The dialog manager is very robust. We've been using it on a number of systems for the last 15 years. It builds off of the ontology. The ontology we generated from the users. It has an editing system where you can build your whole ontology. We did that for the space station, had over 500 different classes and over 1,500 different instances of pieces that we managed through the ontology. The dialog system then generates dialogue from that ontology. So in our view, it's that last 10% that has to be put together for money or for people that are interested to make case something that's available, truly available for doing stuff in NASA's exploration missions. What's next? Well, of course, we're obviously looking at case being used on Gateway, which is like a stationary space system, like HAL 9000 commanded. One of the things that we find a lot in working with different people is they want to troubleshoot the problem. And in order to troubleshoot the problem, they want to know what their choices of action are, and they want to know what the pros and cons of those actions are. We're putting those into the ontology and developing dialogues that help the user understand what's the ramification of making certain choices. And finally, in the last couple of months, Alexa has a development console where you can build Alexa voice systems and then send them to your remote system like Case. We're thinking of using and experimenting with using Alexa as the voice interface to Case. And that's all I have. Thank you for listening.
Thank you. That was awesome. As a software engineer, this is something I've thought about a bit in the past, and I could talk to you for a long time about different aspects and my thoughts on certain things. But I won't do that because otherwise I'll take up all the question time. So maybe we can chat some other time. But Grace asks, what about malicious hacking? Will Case discern an unsafe procedure?
Oh, that's great. That's a great question. Yeah, because the procedure in a database, you think a hacker could get into the database, of course. But it's only as safe as the system that's maintaining all the software. Like at NASA, all of their procedures are protected, but yes, somebody could hack them. One of the advantages of this is that if a procedure is hacked and starts to do something that isn't within the courses of action that are built into the ontology, Case will at least stop and say, this isn't the way you did it last time. Is something changed? Basically, it can at least notify you that something's not the same as it was before because it's run this procedure through simulations a number of times. But having said that, I'm sure there are other ways hackers can get in and cause problems. And I think that's a good thing to be testing and studying as we go forward.
Any other questions? All right, well, maybe I'll...
So maybe you can ask the question you wanted to ask, or at least one.
Sure. I mean, I guess, yeah, so I've thought a little bit about this, and I've come, you know, kind of what I would love, and I'd love to be in the business one day of like running a platform, right, that can operate robots on the moon or something for mining or something, right? That would be fantastic. Yes. And there's, you know, a lot of what you discussed, and I guess one of the things that kind of one of the things I see with robotics at the moment is it's kind of like it's zero or it's you got the 0 to 1 problem, right? You got to put there's a lot of upfront capital to develop the robots and brain power to develop these autonomous systems, and you can't leverage all of that, like any of that, until you get to a point where, okay, it's usable and it can operate fully autonomously. So I see a lot of value that can be captured there if you can develop a system to do runtime, like real-time intervention in robots, and then you can just, if you can build a system that facilitates the runtime intervention of robotic systems, then you can just keep building on top of the macros and procedures until a point where they're fully autonomous. But you're always, probably with robots, you're always going to get to a point where they're going to get stuck on something, right? And it needs someone to intervene. And if you can, you know, build that system that makes that an easy process, you could end up with a situation where, like, initially it's a lot of people controlling things, and then over time you just build the macros and procedures, and over time HAL can take over and control most things autonomously.
Yeah, that's good.
That's just...
It's good because that's probably the way it's going to happen. Nobody wants something to run by itself until it's trusted, until it understands. And like you said, if something goes wrong, you need to be able to jump down there and help it without shutting everything down and starting all over again. So that's very good. I think this comes across as being, you know, a totally autonomous HAL 9000. And of course, it really never works that way. For example, our robots, when they go to move and grab something, if they can't, they stop, and the Craftsman template system that's looking at them throws an exception. It's a safe exception, and the user brings up a screen and grabs the robot's endpoint and moves it and says, now take over from there. And that takes a lot of time and a lot of work, and we have that available. So I don't think you'll ever see something just flat out start. They'll start with, I think they'll do a lot of less teleoperation than we've seen in the past, because lots of things robots can do without guiding it inch by inch with the humans.
Yeah, exactly.
But I still believe they're only going to let it go so far, get to waypoint 1, and when you get there, let me know, kind of thing. And then they're going to work with it until not only it doesn't break as much, but they trust what it will do. And I believe you're right. I don't think you're just going to pull it out of the box, put it on the Lunar hab, and everything starts working. I believe it will be iterative. It'll be interactive with people, where people will supervise lots of it and then slowly back off. I'm going to take this time to mention one thing in my experience. I used to be in the Army Field Artillery, and I was around years ago when they were automating it. And they were automating the fires for a whole battalion, which were like, you know, 150 targets in a few hours. And they had this automation system that would generate all of the solutions for all these targets. But the humans were too worried that they'd hit the wrong target, so they wouldn't let anything shoot until they physically checked it out themselves. And as they did it for 10 and 20 targets, it was slow, but it worked. As they needed more and more targets, a lot of the flight controllers, the flight director said, look, I haven't got time. It's getting a most. Let it go because we're losing the war. And they let it run fully autonomously, and almost for everything, it did what it was supposed to do. It took them a while, though, to trust it, to make sure what it was doing was right. And they finally said, okay, I haven't got time for this. Let the robot do it.
Yeah, I think that's a valid point. Software systems do have to earn the trust of their users too.
Yeah.
We do have to close it up now.
Sure.
It's the end of
Thanks again. I enjoyed the discussion.
Yeah, thank you. Thank you very much.